This is the first webinar that I've ever given, so it's very, very exciting. I feel like I'm back in grad school and asked to give my first talk. So it's a lot of fun. Also, I'm having a chat open in case people want to ask me questions in the middle. So the idea is I'll try to explain some ideas that are highly geometric, they're highly classical, and I know that optimal transport seems scary, so I'll tell you the story behind this. 2 years ago, I said, maybe I should learn some new math, right? It's always healthy to learn new math. And I said, why not optimal transport? That seems pretty cool. And I learned the first, I look at the first 3 pages of the book, and then I try to understand what that means for things that I know somewhat well, which would be, for example, Laplacian eigenfunctions. And I never read the rest of the book. So the amount of optimal transport I know is very, very little. And you'll sort of see it will be very transparent because I'll explain everything I know, and then you know it too. So yet there's a lot of things that can be done. So the motivating picture, or one of the motivating pictures, is always this, and I like to show it because it's so beautiful. So I think I don't need to explain what this is, right? It's the sand on a vibrating membrane. And I'll sort of try to historically start this story, because even historically, what's happening here is quite remarkable. What I'm discussing is a theorem that was essentially forgotten. And so I'll first sort of recap Sturm-Liouville theory, but maybe from a perspective that is not in the textbooks, shockingly, which should be in the textbooks. And I learned about it from a paper of Berat and Helfer from 3 years ago. I have not found many other sources actually discussing this. And then I'll try to explain what it could mean to have a Sturm-Liouville theory in the strongest sense in higher dimensions. I'll explain what's certainly not possible and what one could hope for. I'll give you 2 or 3 slides of optimal transport, just one basic definition. Technically, there's not even optimal, just transport actually, and optimality doesn't even occur. So, and then I'll tell you some results and many, many problems. Okay, so here's a story that I like to tell because I find it so incredibly heartwarming. Everybody should know about the story. So the story is in 1833, so 3 years before the publication of these papers, Legendre dies and he vacates his seat in the French Academy. And there is strong competition. Okay, we have Sturm, we have Liouville, and Duhamel competing for the seat. Now that's intense. And the 4th applicant is Libri-Carucci. Now who's Libri-Carucci? Well, clearly the winner. So he was actually sort of the seat in the French Academy went to Libri-Carucci, and Sturm actually got 0 votes, and Liouville got all but 1 vote. So now you get curious, right? Who's this mysterious Libri-Carucci? What's he doing? What did he do to impress the French Academy so strong in 1833? Well, he seems to have been very well connected, and the story gets more interesting. So in 1841, he gets appointed the chief inspector of French libraries. And he's using his job mainly to steal books, a large number of books. He gets caught, and in 1848, there is a warrant out for his arrest, and he flees to London with 30,000 books that he stole. And so mind you, this is the person who beat Sturm, Liouville, and Duhamel in an election to the French Academy. And then what he does for the rest of his days is he sells the books one by one and lives a very luxurious life in London. Okay, and the story is not over. So for example, in 2010, so 10 years ago, one of the stolen books, which was a letter from Descartes to Martin Mersenne, was actually found in Haverford College in the US, and then returned to the Institut de France. But essentially 200 years later, you still sort of retrieve stolen goods from Libri-Carucci. So he won. 3 years later, Ampère dies. And the election is again an election for who's succeeding Ampère. And what happened 3 weeks before the election is that Liouville gave a talk in front of the Academy praising Sturm, which apparently was a minor scandal in itself because he was supposed to praise himself. But he did not. He praised Sturm and said Sturm's memoirs and Sturm-Liouville theory are comparable to the best work that Lagrange ever did. And on the day of the election, so 3 weeks after this, on the day of the election, December 5th, Liouville and Duhamel both retract their candidacies to make sure that Sturm gets elected because he was their friend. And now Sturm's name is actually on the Eiffel Tower. So that's sort of, I don't know, it's a very heartwarming story. I see Sturm-Liouville theory in a very different light now. Okay. What is Sturm-Liouville theory? So I'll essentially it's if you want, it's the study of eigenfunctions of second-order elliptic operators on the real line or in an interval with some boundary conditions. And I'll not discuss the general theory, but I'll just talk about the trivial problem you can solve in your head. And what you can solve in your head is Laplacian eigenfunctions on an interval with Dirichlet boundary conditions, and those are signs, right? So you know about this. And then there's a theorem, and the theorem is known as the Sturm oscillation theorem, and it says that the kth eigenfunction has k minus 1 roots, and many more things are known, like the roots interlace. So between any two roots of an eigenfunction, there's one of the next eigenfunction, and so on. And this is sort of a classical theorem. It basically tells you that eigenfunctions are fairly generic, operators on the interval. They behave like they do for the Laplacian. The Laplacian dominates as a differential operator if you want. And it looks roughly like a sine up to some things. And physicists know this as sort of WKP expansion, right? There's no subtlety in, there's not a lot of subtlety in eigenfunction expansion on the line. Okay, so this is the book, and it's on all the textbooks. Okay, this theorem is in all the textbooks. It's on Wikipedia. You'll find it everywhere. Now, you start specializing and you look at sines and cosines maybe. And maybe you look at the periodic one-dimensional torus. You get sines and cosines, and you realize there are actually slightly stronger results, right? Because sines and cosines are very, very special. And what you find is you find the Sturm-Liouville theorem, which is from 70 years later. And it's very, very interesting. It's a very nice result. It says that if you take a linear combination of sines, starting at a certain frequency, then no matter how many additional frequencies you add, you can never decrease the number of roots. So on 0 to pi, sine nx has 2n roots. And if you then add additional higher frequency components to it, no matter what you do, no matter how smart you choose the coefficients, the number of roots is not going down. It's a pretty striking result. I mean, it says that any linear combination of sine 3x, sine 4x, and sine 5x has at least 6 roots. That's a pretty funky statement. But okay, you say, okay, clearly this is that's some proof. So I'll give you one proof that's very short, which is you can write f as the imaginary part of a holomorphic function restricted on the boundary of the unit circle. And then what you see is that this thing has at least n roots in the origin, and then the argument principle tells you that you wind around the origin n times, and then you have at least 2n roots, because every time you wind, you cross the imaginary axis twice, which means the imaginary part vanishes. There are a couple of other proofs as well, but this is one proof. And you see it's a very special proof, right? You go to the complex plane, and then it's a power series. It just happens to be a power series, the magic of sine and cosine. So here's, right, so this is what I'm trying to say here. Is you think, okay, surely sine and cosine are very, very special objects, right? They're the foundation of harmonic analysis. I mean, they're not just any functions. So it turns out, with regards to this theorem, sine and cosine are not special. So I'm trying to distinguish this, but by saying, this is the Sturm oscillation theorem that you find in the textbooks or in Wikipedia or in lecture notes. This is the actual Sturm oscillation theorem. And it's much, much, much stronger. It says, unless all the coefficients vanish, a linear combination of eigenfunctions of this differential operator from m to n has at least as many roots as the lowest frequency object, and at most as many roots as the highest frequency object. It's an extreme rigidity statement. It says, you combine 8 eigenfunctions, you can't have less roots than the least frequency object, and you can't have more than the highest frequency object. Absolutely remarkable, absolutely stunning. So why does no one know about this? That's a good question. So I learned about this from a paper that went on the archive, I think 3 years ago by Berra and Helfer, and they say, although well known in the 19th century, the theorem seems to be ignored or forgotten. And when I saw the result, I was just stunned. I'm like, wow, I've looked at sines for a long time, also at cosines. I thought, there's not many things about the sine that are going to surprise me, but this is surprising. And this, this paper by Berra and Helfer is to be recommended. It's a really remarkable paper. They sort of go through the original paper, they give all the proofs, and they even give a timeline. It's a really great paper. And so essentially what happens is the result was announced and then published in the Journal de Liouville. Lord Rayleigh is absolutely excited. He says it's a beautiful result. He knew about it. Pockels knows about it in 1891. Hurwitz gives what's called the Sturm-Liouville result. And he is actually sort of, this result is actually sort of a special case of the Sturm-Liouville framework in a certain sense. And he's sort of referring to it. And then the story gets muddy. So what happened apparently is that Courant and Hilbert, they discuss the Sturm-Liouville problem extensively, but they don't refer to Sturm's papers. They refer to a book that doesn't contain the full result. And then, of course, generations after, people like myself, I go to Courant and Hilbert, right? And sort of that's sort of what seems to, how the information seems to have been lost. It's very interesting. It was also rediscovered. So there's special cases of the result that have been rediscovered, especially for sines and cosines, for example, in PDEs. So the Kolmogorov has a paper on the KPP equation, and there's sort of the result is half rediscovered, half not. So it's an interesting story. Okay, now that we know about Sturm-Liouville theory, like the full version, right, uncovered, what would it look like in higher dimensions? Well, okay, let's start with, again, the simplest possible case. And the simplest possible case is we take a nice compact manifold. Smooth, nice. I mean, you can think of the torus or the sphere, and not much is going to change. It's not going to get harder, and it's not going to get easier. So all the results are hard and interesting, or easy and interesting on the sphere. The manifold is not the problem in a certain sense. Then we have the Sturm oscillation theorem, the weak one, and it says that we have a result on the number of roots. Okay. So how would you generalize this to high dimensions, right? What's roots in high dimensions? And there are essentially two ways of looking at this. So one way is, a root is where the function vanishes. And so you look at the size of the set where the function vanishes. And of course, in d dimensions, it's a codimension 1 set. So you look at the d minus 1 dimensional volume of that set. That's the metric version. But there is also a topological version, and the topological version says, remove the 0 set, how many connected components remain? Okay, so that would be the topological version, and I will only talk about the metric version, but it's interesting to actually have a look at the topological version as well. So what you do is you remove the 0 set and you count the number of nodal domains. And there's a theorem by Courant saying that if you have a nice domain in the plane, and has been generalized in many ways, then the kth eigenfunction only induces at most k nodal domains. And this has been improved in various ways, and it's interesting to see how it's sharp and not sharp. So this would be sort of an analogous statement. And even here, the history is quite remarkable. So you say, this is essentially what this is, right? This is the topological version of the statement that the kth eigenfunction has k minus 1 roots. You pick one eigenfunction and you try to understand its 0 set. Now, what full Sturm-Liouville theory tells us is that you can actually take linear combinations, and you can try to understand the behavior of linear combinations. So also for this statement, it would be a very natural question to ask, right? You could say, hey, you know what? I take a couple of eigenfunctions, I look at a linear combination of those, and I look at that 0 set. Maybe that can have a lot more nodal domains. Or maybe it cannot have more nodal domains, right? Either one is interesting. So what can you do with linear combinations? That would be the full Sturm-Liouville analog of the topological question. So again, here in Courant-Hilbert, you find a footnote. And the footnote says you can actually extend the Courant nodal line theorem. And if you take a linear combination of the first n eigenfunctions, then no matter how you combine those, you can never get more than n domains. And it's referred to a Göttingen dissertation of Hermann about contributions to theory of eigenvalues and eigenfunctions. But this story also has an interesting twist. Gelfand in Russia, Gelfand got interested, and he said, wow, it's remarkable that no one paid any attention to this amazing claim. And Gelfand tried to reconstruct it, and he could only do it in a one-dimensional case where it is Sturm-Liouville theory. So in a one-dimensional case, this is true. Any linear combination of the first n eigenfunction has at most n minus 1 roots. And then Arnold recalls that, being involved in the story, he wrote a letter to Courant, and he says, okay, where can I find the proof? You wrote in 1929, there's 1931, right? There's a footnote. Now it's 40 years later. Where's the proof? And Courant answered that you can never trust your student. And he goes on and says, to any question they answer that it's beyond the problem is too easy to waste time on or beyond their weak powers. Sort of a mean statement. But okay, so So this is the topological version. I will not talk about the topological version. I'll talk about the metric version. And for the metric version, we have Yale's conjecture, which half of which has been proven by Logunov. So essentially, you take the kth eigenfunction, and you assume it oscillates like sort of some nice random wave, and you get some asymptotics, and the asymptotics say it should be like a square root of the eigenvalue. Okay, so we do this, and this is what I call a metric version of Sturm-Liouville theory in high dimensions. Right? You get a bound on the size of the zero set. But it looks like a generation of the weak Sturm oscillation theorem, right? You take the kth eigenfunction and you study its properties. What about linear combinations? What if you take linear combinations of eigenfunctions and try to study the zero set of that? What happens? So this is the main question I'm trying to talk about here. And I think the question is very interesting, but I think the proof is also interesting, and the proof sort of shows you other things, and it also suggests other questions and techniques. So the main question that I'll talk about now is you take a linear combination of eigenfunctions on some nice compact manifold. Again, if you take the torus, just the two torus, take the two torus and the eigenfunctions are trigonometric polynomials, things are not going to get easier. And they're not going to get harder either. Okay, so if you like playing with that in your mind, that's really, you're not missing out. So the question is, what can you say about the zero set? Can you say anything about the zero set? So the straightforward generalization of Sturm's oscillation theorem would be if you add higher frequency objects, then the zero set cannot substantially decrease. It cannot be much smaller than the nth eigenfunction. And this is false. Okay, so it turns out no such estimate is possible. And I'll give you the construction. Okay, so again, let's actually go to the sphere, because the sphere in this case is the nicest. We go to the sphere, and we pick a nice spherical design. A spherical design is a set of points such that the average of the first n eigenfunctions in these points is the same as the global average, which is 0. So these points exist, and the results about how big how many points you need to get n eigenfunctions, that all sorts of results exist. You can also phrase it sort of purely algebraically, because eigenfunctions on the sphere are just restrictions of polynomials onto the sphere, right? Polynomials in R3 restricted on the surface of. So the question is, well, you take these points, and the average is 0. And then you do the following. You take this measure that you've created. You know that the measure is orthogonal to all eigenfunctions. And then, except the trivial one, the first trivial eigenfunction to constants. So what you do is you subtract the constant function 1 from this measure. And you have created a signed measure, if you want, that is actually orthogonal to the first n eigenfunctions. And it's a very simple signed measure. It's just n points. So n Diracs, and the rest is minus dx. Okay. And then what you do is you apply the heat equation. For a very short amount of time, the heat equation preserves orthogonality. And so immediately you have a C infinity function on the sphere that is orthogonal to the first n eigenfunctions. So it is actually of that form. It's exactly of this form. It's orthogonal to the first n by construction. And what does it look like? Well, it's essentially n sort of Gaussians, very narrow Gaussians, and then it's -1 everywhere else. So the zero set of that are just n tiny rings. And the rings can be as tiny as you want by letting the heat equation run for a short enough time. So you get it. So basically, this gives you a function on the sphere that is orthogonal to the first n eigenfunctions and has an absolutely tiny zero set. Okay, so it looks like all hope is lost, right? Because here's the counterexample. And well, okay. So there's no analog of strong Sturm-Liouville theory. But what if you allow to let the estimate sort of depend a little bit on the function? Can you then say anything at all, right? What's possible? And if you think about it for a while, something has to be doable. Something has to be possible. And I'll give you the motivating picture. Suppose we have this function on the two torus. So here's a beautiful, nice periodic two torus. actually, maybe it's not a 2 torus, maybe it's more like, oh, we can make it a 2 torus. Okay, it's a 2 torus, and with a function, the function just maps to -1 or 1. Super easy function, right? And you see it has a couple of nodal domains here, not too many. The 0 set is not gigantic, right? Maybe it's 20, right? Not big. This function is not orthogonal to all trigonometric polynomials with frequency up to 10 to the 10 to the 100. It's not. There's no way, right? I mean, this is a fairly simple function. It's got pluses somewhere, it's got minus somewhere, but it's not that complicated. It's not that focused, right? Also, if you go back to the original sort of sphere example, right? In the sphere example, what you have is you have this Dirac measures. You cook them in the heat equation for a very short amount of time. If you do this, if you cook a Dirac for a short time, you get a very, very tiny Gaussian, which is the goal, but the very narrow, tiny Gaussian is also very high. The L infinity norm is gigantic, right? It's actually, you know, as time goes to 0, it's singular. So it's a very big L infinity norm. So the question becomes, well, maybe if the norms work out, if it's not too peaky, if it's not too spiky, if it's sort of flat, like this function, maybe something's possible. Any questions up to this point? I'm also in the chat if someone has.
Could you just repeat the definition of spherical design?
Ah, right. So a spherical design is a set of endpoints on S2. So in general on the sphere with the following property, a Laplacian eigenfunction, the first few Laplacian eigenfunctions, when you average them in these points, so you take these points, you look at the Laplacian eigenfunction, the point, and you average these values or sum them up, then it's 0. So essentially sort of balanced points that sort of equally capture plus and minus of the Laplacian eigenfunction. And they're quite beautiful. So on S2, on the 2 sphere, it's actually sort of, if you inscribe a cube or a dodecahedron or an icosahedron in the cube, then these points are actually very good points that actually have average value 0 for the first view. So that's the construction. I'm sure there must be many other constructions of this type, right? What I want is essentially, I want that the average of, I wanted the sum of Laplacian eigenfunctions evaluated in very few points to be 0. That's sort of, if you have enough points, it's an underdetermined system of equations. So this can always be done. But it's not crucial for the next few steps. So it's sort of a counterexample.
Stefan?
Yeah?
I wanted to ask, if you have a linear combination, in the real analytic case, there is an upper bound by Jerison, right, on the size of the nodal set?
I think it's finitely many terms, right?
Yes, I think so, yes. It's not as strong as the Sturm-Liouville, but...
Right. Right. So yeah. So there's also one by Donnelly, I think.
Okay, yeah.
There's something from the 9th. There's some. What's the difference here is you actually go all the way up to infinity.
Okay.
And this is, I will not say that this is more. So whether this is easier or harder is a question, because to some extent, you can interpret this question also differently, right? I mean, this is really, what is this object? It looks complicated. It looks imposing, right? But it's not really, because what it is it's a function that's orthogonal to the first n eigenfunctions. I mean, take a function L2. It can be expanded in eigenfunctions. And this equation just says that the first n coefficients are 0. So what does a function have to look like if it's orthogonal to sine x, sine 2x, and sine 3x? I give you a function. I tell you it's orthogonal to sine x, sine 2x, and sine 3x. What do you know about the function? That's the question. So that's whereas the Jerison and Donnelly approach with finitely many combinations is sort of structurally very different because it's finitely many. So you're also orthogonal to the infinitely many ones afterwards.
Yeah. And there are some estimates on the rate of decay on triple products, right? And so if you assume something that you have a linear combination, it like by Bergerath-Cvetkov and some things before them, right?
Right.
Then, so if you assume something on the size of Fourier coefficients, maybe this could give you something. But on the other hand, that's like too specialized to.
So these techniques, the techniques that I'll explain here, are actually structurally very different, and to some extent they're much simpler.
Okay.
So the amount of analysis that goes, like hard analysis that goes into this, is actually very small.
Thank you.
Absolutely. Thanks for the question. Other questions?
Yes. Excuse me. Do you assume the coefficient to decay fast enough for the function to be smooth? Or
right. That's a good question. So to some extent, the smoothness is your friend. Like if it's very fractal and crazy, probably has a very large zero set. So what I'm really assuming is that the function is, I think, continuous. So I want the function to look like this and be continuous. So I'm not assuming anything on the coefficients per se. I assume that the function itself is continuous so that I don't need to worry about defining a zero set.
Okay.
If the function is a bit rougher than continuous, you can actually define everything in terms of a heat flow going to zero. So if you have, for example, a function that's +1 and -1 and never zero, right? Then you can't see anything about the zero set. But if you apply the heat equation for a short amount of time, it creates the zero that you're looking for. So all the results have an extension to a function doesn't need to vanish if it's not continuous, right? It can be just +1, -1. But you can create a notion of zero for those functions, and then the theory carries over 1 to 1. It's just a modifying argument if you want, not to modify. Cool. Other questions? Sum is from k greater than. I don't get the question. So the sum runs from, oh, sorry, now I get the question. Right, sorry, the index is n, but it should be k. So sorry, we start at n and then we sum all the way to infinity. I didn't get the indices right. Cool. Okay, so here's the result, okay? Here's a result that says that this is actually possible. So if you take a continuous function that's orthogonal to the first n eigenfunctions, the zero set cannot be too small. And what do I mean by this? I mean, there's a square root lambda, which is the eigenvalue corresponding to the lowest frequency object. So that's exactly the analog of Sturm-Liouville theory in a sense. The lowest frequency object gives you sort of the oscillation bound. There's a logarithmic loss. And then there is something that depends on the function, and it measures, in a certain sense, how spiky the function is. So if it has a lot of peaks where it's very large, then this is a very small quantity. And this sort of compensates for the artifact that we see from the other example. So yes, results of this type are possible. And the question is, what's the sharp form? So the idea is, what do you know about an object like this? Not very many things, because it's actually quite general, right? It's just, you just orthogonal to the first n eigenfunctions. It's a very implicit kind of statement, but it also means that if you apply the heat equation to it, it's going to zero quite quickly, right? Because high frequency eigenfunctions go to zero quickly under the heat equation. So this object goes quickly to zero if you apply the heat equation for a short amount of time. And that's the information that's sort of in the proof, because the heat equation sort of just mollifies things and moves them around a little bit. And if it's then, if you move things around a little bit and you're very close to zero already, then the plus and the minus sort of have to cancel. And if you look at the sort of two torus, or really, Logunov's result, if you want, the square root lambda is actually sharp. Like, you couldn't hope for a better exponent here. The exponent here is probably not sharp. The 2 minus 1 over d is not sharp, I'm pretty sure. And there's a recent paper by Carol, Massaneda, and Ortega Cerda, who, and they removed the log completely. The log's gone, which is actually...
Lambda here?
Hmm?
What is lambda here?
A lambda is the eigenvalue of the lowest frequency object. So you start summing at the nth eigenfunction, which has eigenvalue lambda.
Lambda is lambda n.
Yeah, lambda n.
Thank you.
Should be lambda k probably. I'm sorry about mixing the indices. Okay, so I think that's pretty interesting, because suddenly you have, it's a new kind of result. It's it's almost an inverse problem, right? You're orthogonal to n eigenfunctions, and there's still information you can recover. Okay, so the conjecture is that you can actually get probably L1 over L infinity, and that would be sort of sharp. And this is known only in 2 dimensions. And that was an argument that comes from optimal transport. Did removing the log keep the same exponent on the ratio of norms? This lambda is sort of, there's 2 independent factors. One of them is what's the oscillation, which gives you some sort of, if you sum up high frequency objects, there's a lot of oscillation. That's capped by the squared lambda term. And this is a scaling invariant quantity. So somehow they play different roles. So the log does not impact this term somehow. Okay, so I'll get the optimal transport. So this was quite striking. And actually, I've sort of started thinking about all sorts of things in optimal transport, because there's an interesting confluence of fields. And the idea is actually quite simple. So I'll give you, as far as I got, I think I got the first 2 pages of the book, and that's all you need. I made it all the way to the definition of a Wasserstein distance, and not even optimal transport. So the problem of optimal transport is sort of quite simple. Beautiful drawings, as you can see, emulating a good blackboard atmosphere. So suppose we're having 2 measures, okay? So mu is a measure and nu is a measure, and they have the same total mass, which we can assume is 1. So here's a nice sort of probability distribution, looks a bit like a semicircle maybe, and here's some sort of uniform distribution. And the question is, how do I best transport one to the other? And that sounds a bit, you know, what does it mean to transport a measure? And it means the actual literal physical transport. So I will only talk about the Wasserstein 1 distance here, which is also known as the Earth mover distance. And it's actually the cost of moving the Earth. So assume I have a measure, and a measure is really built up of little epsilon boxes, right? I can build, say, you know, assume the measure is absolutely continuous, right? And essentially it's a little epsilon boxes of measure and other little epsilon boxes of measure. And then I take a box and I put it to another box. I transport it where it should be. And the cost of transporting a box of weight epsilon across distance delta is exactly delta times epsilon. That's it. So it's almost a physical, you know, if you yourself had to carry these boxes, right? This is sort of the boxes you have, and this is the boxes where you want them to be, and you have to physically carry them yourself. This would actually be the physical cost, right? It's, I'm not good at physics, force times distance or something. I don't know. But actually, you know, or if a truck drives these containers to where they should be, it's actually the cost of gasoline. It's proportional to gasoline cost, I guess. So, okay. So this is optimal transport. Any questions on this? It's really just transport. It's how much does it cost to move on to data. In 1D, I would say in this case, actually the cost is sort of independent because there's a fundamental theorem of calculus going on. But this is sort of a problem in 2 dimensions, right? So here we have, what we have is we have blue boxes, blue circles, and we have red triangles. And assume that the triangles are sort of boxes of density 1, right? It's just all sorts of boxes. And I want to move them all into the blue areas. You could think of the triangles as you know, water tanks, and you could assume these are swimming pools that need to be filled. Then how do you move the water from the water tank to the swimming pool? What's the best arrangement, right? I mean, here you have a big, down here you have a big triangle. Probably you should try to use it to fill maybe this one here, because this tank over here you can fill with the other one, right? But it's not an easy problem. It's not clear. Even the existence of a solution is not a priori clear. But okay, this is the field of optimal transport, studying properties of this and trying to understand what's going on. And something that the sort of analysts seem to have not done very much, which is extremely interesting, is how about you take a function that's mean value 0? So you take a function f, say even on the 1-dimensional torus, of mean value 0, and you say there's a positive part and there's a negative part. And the positive part is a measure, and the negative part is another measure. What's the transport cost? Like the 2 measures have the same mass because the function is mean value 0. How much does it cost to transport one to the other? I don't know many good bounds. I don't. And I think it's quite interesting. And trying to understand this better has led to the result. So, so 3 years ago maybe, I started playing around with this, and I tried to understand things, and the following inequality popped up, which I think you can prove sort of by hand, but sort of nice intrinsically, and it's philosophically the kind of statement we want. If you have a function from 0 to pi with mean value 0, say continuous, okay, it's a continuous function, mean value 0, then if you multiply the number of roots that it has with, well, this is just Fourier coefficients divided by k squared, so it's the L2 norm of the integral of the function, then this is not too small. There's a bound like this. And essentially you can see this is sort of sharp, this estimate. So you take sine nx, then this is roughly n. You only have one Fourier coefficient at frequency n, and that's 1. So you get a 1 over n squared and the square root. So you get a 1 over n times 1 over n, and here you have factor 1 on the right hand side. So it is sort of, it's sort of optimal along frequencies. And in particular, it also gives you some sort of strong Sturm theorem, because it is a function that's comprised only of high frequencies, right? If your function is built up exclusively of high frequencies, this is going to be a very small object, because the high frequencies get downweighed very much, right? You divide by number. So this is actually a lot smaller than the L2 norm, and you get some sort of statement like this. And it's also one of very few lower bounds on Fourier coefficients. So this is one of, I've been worrying about this for years and I never get very far, but I think, you know, there need to be better lower bounds on Fourier coefficients, just for inverse problems. You need to know that, sometimes you need to know that Fourier coefficients are not too small. Like smoothness of a function gives you upper bounds, but in particular, if you know anything like this, let me know. And to prove this statement, though it's, I think it can be proved by elementary means. The original proof I found, I didn't even look for this. I was looking for something else and this came out. And the thing I looked for was optimal transport on the one-dimensional function space. So just one-dimensional functions trying to transport them. And this is sort of the philosophical beginning of this. And then it took me a while to realize that that's not really what I want. What I want is something like a Wasserstein uncertainty principle. And here's one instance of it. It says if you have very few post offices, then you know, the mailman has to go large distances to get you the mail. And if, you know, letters arrive all the time and very quickly, then presumably there are a lot of post offices and a lot of mailmen. And I'll try to make this precise now. Here's one way of making it precise. So this is the two-dimensional case. So suppose you have a function on the unit square, say continuous function on the unit square, mean value 0. Then I say that the f plus, the part where it's positive, I call the post office, right? It's the surplus of letters. And everywhere where people were waiting for letters, I would call that f minus, right? It's the demand for letters. And then the question is simply, how much does it cost to transport the letter from the post offices? I guess there's n letters at the post office and n letters that we want. How much does it cost to transport these letters? And the idea is quite simple. The idea is, if this is a very small quantity, if it's very cheap to take the mass from the post office to where it's needed, then there have to be many post offices. And if there are many post offices, then there has to be a large zero set, because a zero set is the transition from a post office to a non-post office, if you want. Right? It has to be zero set. And conversely, if the zero set is very, very tiny, then there can only be very few post offices because they eat up all the zero set, and it's going to be quite expensive to transport the mail. Okay, so this is the statement. And here's some sort of idea behind this. So suppose here the blue is sort of the population, right? Suppose this is a city. It's a nice city, and then you have 4 post offices and they're red. Then what's the best way to transport the mail? Well, probably the one down here transports over here, and the one over there transports down there, and these transport up here. But it also means, since there is a demand here, right? It means that the function is negative here and it's positive here. There probably has to be a zero set. Or by continuity, there has to be a zero set, and it cannot be too small. And I assume that the best case, the one that has the least transport, is actually quite simple. I assume it's just post offices that are balls. And then just around it, there's some sort of circles where people live as close as possible. So it's an annulus around the ball where people get as quickly as possible to their mail. So I think there's some cities in the world that are actually organized in like rings, right? So it's sort of that kind of principle. And then how many post offices do you have? Well, it's just the scaling between the isoperimetric quantities, right? How many you want. That can be done by hand, sort of. But you know, it shouldn't be too big, right? Because then it's expensive to transport. But if it's too many, then the surface area is too big, and there's probably a golden region in the middle. So that's the idea. And that's a very nice, very friendly, fairly accessible isoperimetric principle. It makes a lot of sense. It's physically motivated even. But I don't know how to get exactly this. I know how to get it in 2D, and in 2D the full result is known and it's sharp. Higher dimensions, not so clear. So what's different between 2 and higher dimensions? I can tell you in 2 dimensions, it's actually a pretty simple argument. It says if you have a domain, here's a domain. Suppose, think of this domain as a post office. Okay, so it has too many letters. Then how big can the epsilon neighborhood of a post office be? Those are the houses that are just nearby, right? The house is just very close to the post office, very friendly, very easy to transport. And in 2 dimensions, there can't be too many, right? So the epsilon neighborhood of a sort of a nice connected set in the plane is actually proportional to epsilon times the boundary, length of the boundary. It's not bigger than this, unless epsilon is a lot bigger than, right, then you have balls. But if epsilon is very tiny, then, you know, it's not a gigantic area. There are not 10 trillion houses close to one post office. That's the way geometry works in the plane. And in higher dimensions, this is wrong, right? Because you could have a post office that's essentially a very long, thin cylinder. And it's so thin that it basically has no surface area at all. But the epsilon neighborhood is then an epsilon cylinder times something very big. So it's the usual kind of problem you get when going from 2 to 3 dimensions and you do potential theoretic arguments. The scaling of surface versus boundaries is off. So this is why I don't know how to prove anything strong in high dimensions.
And if you assume metric is real analytic, because like Donnelly and Pfefferman were able to, you know, prove Yale's conjecture in the real analytic case, and you have exactly the same obstacle, right, on higher dimensions, these cigars.
Yes. But Donnelly and Pfefferman, they work on a single eigenfunctions. And single eigenfunctions are sort of, this is why I think it's also sort of, you know, it's a different problem in the sense. Single eigenfunctions are extremely rigid. And Donnelly and Pfefferman, they use the real analyticity to sort of, you know, recover the intrinsic rigidity of the eigenfunction. Here, the objects we're looking at are not rigid at all. I mean, these functions here, right? If you look at sorry, that's too far. Okay, if you look at objects like this, they're not rigid. That's actually an infinite dimensional function space. Like you do actually calculus of variations over infinitely many possible combinations. These functions are just orthogonal to n integrals. Like n integrals are 0, that's all you know. So these objects are not rigid at all. So I don't think analyticity helps. I don't think the smoothness of the metric makes any difference. I think this is essentially one basic isoperimetric principle at work. And once one understands this fully, you'll have a complete understanding.
Thank you.
Okay, so how does this connect to Sturm-Liouville theory, right? Well, what's the connection? And the connection is very simple. What do we know about a linear combination of high frequencies, maybe infinitely many high frequencies? It decays quickly under the heat equation. The heat equation is actually transport. It's a form of transport, right? The particles move around in sort of this Brownian motion fashion, but you know, if I have a coffee cup here, right, and if I put a candle under it, then the heat's actually transporting through the material, right? It's actually transport. So what I found, using the fact that the heat equation decays quickly, is I found a transport map, and that maps the positive to the negative mass. And I can bound the cost of this by knowing how much heat equation particles travel. Like it's bounds on the heat kernel. It's not tricky. It's very, very straightforward argument. It's like half a page. So what we get is we get an upper bound on the transportation cost. We don't get the optimal transport. The heat is not going to be the optimal transport. There's no way it's going to be the optimal transport. It's a transport. And this here is the best possible transport. So we have an upper bound on this. So we get a lower bound on that. That's it. That's just it. So this is how these objects talk to each other. And we basically don't use anything about eigenfunctions except that linear combinations of high frequency eigenfunctions decay quickly under the heat equation. And there's not much more we can use because it's not a rigid object. So I'll quickly summarize. So in higher dimensions, Amir Sageev and I, we tried to get a result in high dimensions, and we got one. And it's this, and we have a power of 4 - 1 over d. And then in March, Carol Massaneda and Ortega Cerda actually improved this, also in the paper where they removed the log. A very nice paper, and they get this down to 2 by sort of an improved argument. And what you really want is you want 1. You want power 1, and we have power 1 in 2 dimensions, and the proof is not terribly difficult. I basically told you the proof. There's not too many houses close to a post office. It's against a 3-page argument, maybe, and it uses elementary geometry. What's the bound? It's isoperimetric inequalities. Okay, I'll quickly explain the proof, the spirit of the proof, just to see how low. So you see how low tech this is. It's low tech because I don't think many people have looked at these sort of notions. Not much is known. Everything's very early stages. So here what we do is we take the unit cube, we decompose it into many little boxes. This quantity tells us that, you know, the function can't be 0 in all the boxes, right? This tells us in how many boxes there's a non-trivial amount of function. What's the smallest number of boxes that has something in it? Either supply or demand, too many letters or a desire for letters. And any box that is, you know, not empty, that has something happening, well, there's two cases. Either there is mainly supply or mainly demand, meaning the function is either positive or negative, fully, almost fully. Well, if it's almost positive, like if there are too many letters, you have to transport them somewhere. And when you transport them outside the box. Gives you a lower bound, right? That means you have transport costs. The transport cost is non-negligible. If you have a box that has roughly the same amount of letters as desire for letters, right? If it's sort of evenly split, then of course the transport cost in that box is almost 0. In fact, it's you know, it's just maybe the length of the box, right? It's very tiny. But that means there's a 0 set, right? And then you get a 0 set. And in particular, if you have a, for the second case, we use the relative isoperimetric inequality. It says if you have a subset of the unit cube, then the amount of boundary satisfies an isoperimetric inequality. And the interesting thing here is that the boundary inside the cube, not on the surface, or not on the boundary of the cube, but the boundary of the subset omega strictly inside the cube. That's not too small either. That's what we use. Okay, and I'll finish with sort of a simple byproduct. So here's an example of what an eigenfunction, a linear combination of eigenfunctions could look like, or this is a chaotic eigenfunction on the 2 torus. So what you could ask is, how well do they do with supply and demand? Right? The Laplacian eigenfunction is actually a mean 0 function. There's a positive part and there's a negative part. And how much does it cost to move the positive part to the negative part? Are they maybe they're naturally good ways of designing sort of post office distributions, right? You could sort of wonder about this. And what I got 2 years ago is, yes, there is actually, it's almost the right result. It's, you know, the amount of mass that needs to be transported times the wavelength. Because you assume that next to every big plus, like every big positive part, there should be a negative part nearby, right? And then the transport should be cheap. It should be exactly 1 wavelength in length. And then again, in this beautiful paper, the log here was removed as well. It's the same log actually. So the remark was removed. So this is a sharp upper bound. And this tells you if you want to take the positive parts from an eigenfunction and move it to the negative parts, you can do this very efficiently. It's pretty cheap, actually. It just costs you a wavelength. On average, you have to transport a particle only, an average letter only travels a wavelength, which is an interesting geometric quantity, interesting geometric information about the eigenfunction. I don't even know a bad lower bound on this. One would assume that it's maybe sharp, maybe not, hard to say, but it's sort of, you know, the proof is, again, the proof sort of follows out of these other principles. Okay, and with this, I'm done. Thank you very much.
And thank you very much for this talk. Do we have any questions for the speaker?
Stefan, do you think that the gradient could be a good heuristic of how to transport?
Absolutely, absolutely, absolutely. So, right, great question. So, right, if the gradient, right, you want to transport along the gradient.
Mm.
Right, yes. Yes, I don't know how to make it precise, absolutely.
But when you're saying if there is a maximum and minimum nearby, then the gradient is large, and so that's how you would, heuristically, that's how should give you a way to transport.
So there are some results on, like, you know, you have random analytic functions and you transport Voronoi cells like created by nodal sets to the roots and the zeros, and I just don't know. Another question that I want to sort of, another question is very natural here is, everything I did was in terms of L1 and L infinity. Why? Well, because the proof works out this way. I'm not even sure there are right spaces. There might be much better results if you go to like a critical LD, LD over 2, I don't know, BMO, I don't know. So there's a lot of stuff that's open
All right. Thanks. Thanks, Dima, for this question. Do we have any
Yeah,
other?
I have a question. If that's okay.
Yes.
So the last remarks remind me of this idea of spectral optimal partitions, that the nodal partitions are somehow optimal. So can you say something about optimality? So these partitions, nodal partitions, and eigenfunctions are somehow optimal in terms of Wasserstein metric.
I mean, to some extent, this result says exactly this. So what we have a function with a certain L1 norm. That's the L1 norm, and we know that the size of a nodal set we expect to be a wavelength, and this says that you can actually optimally assign mass. You can transport the mass optimally, and it costs you exactly this. It costs you a wavelength. You don't have to. So basically, what it means is, for every time there's a positive part, there's a negative part nearby that almost exactly matches it in terms of total size, right? If you think of a sine wave, then it's exactly this, right? You transport each positive part just one period over to the corresponding negative part. Of course, two-dimensional eigenfunctions and high-dimensional eigenfunctions, they're not sines. They're not nearly as regular, right? They're like big bumps, and then there's like tiny bumps nearby. But this principle here tells you that, in fact, this is not a problem. In fact, you can actually match the positive and the negative part. You can do some sort of bijection between the masses such that no one has to travel very far. I mean, you can also, like, an analytic version would be if you integrate an eigenfunction, high-frequency eigenfunction on a disk, the value is almost zero, right? This is another instance of this.
But I think this is a kind of an opposite claim. You're saying that the eigenfunction is such that there is optimal transport.
Right.
The question is more like, can you show that any nearby perturbations of the nodal set and the eigenfunctions would have a worse transport properties?
I don't think that's true. I think what this shows is, I think they show that the eigenfunctions are optimal in terms of scaling. I don't think they're going to actually give you the optimal partition. And I think the optimal partition here is actually depends on the problem you look at, right? But the optimal partition is probably, in 2D it's the hexagon, right? And eigenfunctions probably don't do exactly this. They do something very close by.
Yeah, basically because there is bipartiteness. The hexagon would not alternate signs, but here
right.
you must have alternate signs.
But to some extent, I mean, it is an optimal statement, right? It says among all functions that oscillate at a certain frequency and have mean value 0, the transport cannot be cheaper than this.
Yeah,
it cannot, and it is at the minimum. So they are optimal in this regard. But at the level of constants, I don't think so.
Mm-hmm.
Yes, Stefan, I have a question. Good to see you.
Good to see you as well.
Yeah. All right. So, you talked about basically compact, Riemannian manifold, and then, for example, in the case of torus or sphere, there's no boundary condition. But then, of course, there's a other situation where you have a Dirichlet or Neumann boundary conditions. And then I'm curious to hear the dependency on the boundary conditions of all these problems you talked about.
Neumann, nothing changes. So if you have a Neumann boundary, all the results are exactly the same.
Okay.
I never thought much about Dirichlet, to be honest. I assume there is a version for Dirichlet that's going to be exactly the same, but I wouldn't know how to prove it maybe right now.
I see.
So Neumann, you're fine.
I see. Thanks.
Yeah, thanks. So I had a question myself. You mentioned at the beginning the topological version of the theorems. Is there a profound reason why the optimal transport approach would not be able to say anything about this, or is it just that you haven't yet attacked this question?
So if I say it's not possible, right, then there's going to be a paper on the archive in a week proving me wrong. So I'm going to be dangerous with such a claim. Here's the problem I see. Optimal, to some extent, you think of the mailman at the post office, right?
Yeah.
So what could happen is that the neighbor holds my mail. that doesn't introduce a lot of transport. So put differently, if you have a lot of like tiny nodal domains that are just absolutely tiny, right? Then I don't see the transport doesn't see it, right? Because they're so tiny that even though you have to transport out of them, you don't transport a lot of mass. It's 1 or 2 letters, right? So it doesn't really contribute much. So I don't see how to get this fine property.
Yeah.
Also the transport, right? If you think of a shape like the letter U, right? And the complement, and you want to transport from the letter U outside, it costs a certain amount. But if you remove the U, if you remove sort of the connectedness of the U, you remove a line. The transport doesn't change, not really, right? So I don't know how to get topology out of this argument. I only know how to get sort of mass and distance.
Yeah, I see. And yeah, I had another question relating to the optimality of the exponents. The example you gave to show that we can't find a unconditional lower bound were these spherical designs, right? There are eigenfunctions on the sphere that saturate the L infinity bounds by being basically very large around some points. Have you checked that what kind of exponents one could get by using a linear combination of, say, a low-ranking eigenvalue and a sequence of eigenvalues saturating these L infinity bounds?
Right, right. That's a great question. So
eigenfunctions, obviously.
Right. So I mean, this is very close. And so for example, you could modify the approach here as follows, right? Especially on the sphere. You could say, how about you don't go all the way to infinity, you just go a little bit. So back to this Cherysson regime, right? So what this gives you, it gives you a subspace of functions and linear combinations of these functions. And as you said, the L infinity norm cannot go crazy.
Yeah. But
so maybe you can sort of get slightly improved results in this regime. That's number one. Number two, I think, you know, if you take the L infinity the saturating one, the North Pole, South Pole eigenfunction.
Yeah.
It actually has a large zero set, right? It actually oscillates along these rings.
Yeah.
So there might be better results on the sphere. I don't know. If you restrict the range. If you don't restrict the range, if you let it go to infinity, if you really allow to take an infinite combination of eigenfunctions starting at a certain index, you won't be able to improve the results substantially on the sphere because the problems are universal in a certain sense. The spherical design problem is on the sphere, right? The counterexamples are on the sphere.
Yeah, I mean, what I was thinking was basically find a way to saturate the exponents that you get for the ratio between F1 and F1 and L infinity norm using these by basically combining something that would be, so this eigenfunction will oscillate very fast around the equator, but at very low amplitude. So if you combine this with a low frequency eigenfunction that is large around the equator, so that these zeros don't become zeros around the equator. So I mean, I was wondering if such construction was trying to saturate to figure out whether this exponent is actually optimal or not by trying these explicit examples.
And so the example that gives you the optimality of the exponent is actually you take the spherical designs, and then you take. It's not a rigorous proof. I don't have a rigorous proof that this is short, but you take the heat equation for a short amount of time, and then you move all the mass nearby. So it's really this annulus type of structure, right? So you have this, if you want, this type of structure. And this is sort of also like, if you think about it, this is sort of how cities are built, right?
Yeah.
You have a post office and a supermarket and something, and then you have like the suburbs, and then you have nothing in between. So in some sense, this is actually how people, like, maybe we live like in cities because of this principle, right? We want to minimize the amount of steps we have to take every day, right? So I think this is the optimal example. Although if you ask me now how to actually rigorously construct a function that looks like this on the sphere and is orthogonal to the first n eigenfunctions, I'm not exactly sure how to do it. There's probably some sort of Brouwer fixed point argument to show that if you have enough of these little balls, right? And you want to be orthogonal to n equations. You want to have n equations be zero, n integrals. And you have enough of these balls, you have more variables than equations, and you should be able to satisfy it. And I'm sure you are able to satisfy it. I just don't know how to prove it.
Yeah, yes. Thanks.
Stefan, I wanted to ask, is the estimate should probably also work on a graph, right?
Great question. Great question. So yes and no. And the idea is the following. You need at some point some sort of isoperimetric principle, right? You need to make sure that, the transport needs, you need to call, if the graph is nice.
Suppose it's an expander.
Then it's going to be quite horrible because it's actually super cheap to transport anything anywhere else on an expander.
Ah.
So it's not clear to me what happens. But if it's not an expander, if it's a planar, basically, if the volume of a ball around a vertex grows polynomially, right, and not exponentially like expanders, then yes, probably there are arguments of this type. There are probably statements of this flavor. And probably, actually, fun fact, the eigenfunction arguments, right, the ones that say linear combinations of eigenfunctions, they don't care about the geometry. I am sure they work on graphs. I'm not using much. I'm not using the fact that the heat equation goes to zero quickly. This is also true on graphs. Nothing changes. The only thing but you need a different principle. So actually, in the paper that Amir and I have, in the last section, we sort of say, it would be really interesting to understand what's happening on graphs, and we don't. But the argument that goes from the Wasserstein transport principle to statements about linear combinations of eigenfunctions, that part uses so little, it works on a graph. I guarantee you it works on a graph.
And sort of a different question. Suppose you want to transport the cube of the positive part to the cube of the negative part.
The third power, you mean?
The third power, yeah, because you preserve the sign, right?
You preserve the sign, but you don't preserve the mean is not going to be zero, right?
But they can be roughly balanced. There are some results.
Absolutely no clue. Great question, no clue.
Okay.
I also agree. I agree that there should be statements of this flavor.
I mean, maybe you could use like a different WP, not W1, but
maybe
I don't know.
Maybe it's a different.
I have no idea.
Do you have a diffusion process acting on the third powers that you can control? That's sort of the question. That would be my argument. But I agree that in terms of the underlying principle just says that the pluses and the minuses of an eigenfunction are near to each other. They're close by, right? And that should then also be true for the third power. Maybe not as good, right? Maybe they're not quite as nearby, but roughly still.
Thank you,
Dima, for these questions. Are there any other questions for Stefan? Well, I think we can thank you for introducing us to optimal transport and to the to their links to eigenfunctions. So thanks again, Stefan, for this talk.
Thanks for the invitation. It was a lot of fun.